Hey, Physics 20s. Hopefully you're doing all right today. Um, Again, you might notice with this, we're actually skipped ahead. We're looking at lesson 9. I mentioned that right at the end, and it's also in our Google Classroom, but hopefully you're not confused about that at all. So we're actually skipping right to the end, checking out lesson 9, because we have talked independently about all of Newton's 3 laws of motion. You might want to put the video on a bit of pause here and just review those 3 laws of motion for a couple seconds. So I'll give you a bit of time to put that on, put it on pause, and review the 3 laws of motion that we've talked about. Cool. So I actually put it on pause there as well. And as you can see on the board, I wrote out our 3 laws just in very, very shorthand in my own words. So first law is dealing with the net force is equal to 0. When the net force is equal to 0, we've got a constant velocity. And things that are in motion like to stay in that exact same motion. So also dealing with inertia there. Second law that we've got here, the second law is when the net force is not equal to 0, we have accelerated motion, and then my net force is directly proportional to my acceleration. And what we're really talking about there is that they're in the same, I'm even going to write that out, same direction. Make that a little bit neater. So the net force and the acceleration are always in the same direction. And then finally, my third law of motion, I shouldn't say my third law of motion, Newton's third law of motion is equal but opposite forces. So if A pushes on B with a force of 20 newtons, B pushes back on A with an equal but opposite force. So again, an opposite objects is something that's kind of important there. Cool. So this lesson, now that we've got those under our belt, this lesson is explaining stuff using 3 laws. So using those 3 laws. So here's a painting of Newton doing all kinds of stuff. He was actually quite the scientist. If you want to look into it, an interesting person and quite a brilliant mind. It's a cool history piece with Newton. But we're sticking to what we need to know. And honestly, with this one, you could explain like almost every part of your entire life, from brushing your teeth to driving to school, um, brushing your teeth to throwing a ball for your dog. There we go. That's a little bit better. Um, like every part, and you'll see that as we go through, I hope. So you don't have this one. I'll just kind of walk you through the first one. So things that you need to do with this is you need to be able to talk about the parts of the motion, the laws, and how it applies to this particular situation. So you've got a car that is initially at rest, and then it accelerates forward until it reaches a velocity of 60 kilometers per hour. Then it moves at a constant 60 kilometers per hour, and then it smashes into a wall and comes to rest. So from rest, accelerates up to 60, then drives at 60 for a little while, so drives at 60, and then smashes into the wall. We want to be able to explain all 3 parts of that. So the first part, when it's speeding up, we could talk about this in a whole bunch of different ways. We'll talk about a few of them here. So I could talk about Newton's third law. I could say that the tires are exerting a backwards force on the ground. So then what would the ground be doing to the car? Be exerting a forward force on the tires, and the cars would move forward, right? Or the car would have a force pushing it forward. Perfect. So that's Newton's third law. So we've explained what law it is, and we've also used a little bit of language for this particular example. We could also talk about Newton's second law for while it's speeding up. So the car is now accelerating in the same direction as the net force. That's the force that's coming from the ground, which is causing it to speed up from rest. Right, so this first little bit, we can talk about either Newton's second law or Newton's third law, or both realistically. The second part is where it's moving at a constant velocity. That's 60 kilometers per hour. So constant velocity should speak to you. It should say it's Newton's first law. So the net force must be 0. They must balance out. And that's how we're moving at that constant speed. So you could even take this a bit further. We've got the force of the ground forcing the car forward. We've got the force of air resistance pushing it backwards. Those cancel out, and those give me a net force of 0. So again, we're explaining this particular situation using Newton's laws. And then finally, the car hits the wall. So first thing that most people would think about here is Newton's third law. So the car is exerting a forward force on the wall. Well, how does the car get smashed then if the car is forcing on the wall? Well, the wall is exerting a force back on the car. So that's kind of what we see over here. The car is exerting a force on the wall is exerting our force back on the car. We could also talk about this in terms of second law. Well, now the net force is going to be backwards. Now the bigger force is going to be the force of the wall on the car. The acceleration is going to be the same direction as that net force, so there's going to be a backwards acceleration causing the car now to slow down. Cool. So that's not so bad. It's again, like this whole thing comes down to saying which law applies and then using that law to describe the motion. So your example that you've got for this, and we've only got one example and then a handful of practice problems. Your example is a ball is thrown straight upwards into the air. So using Newton's laws and force diagrams, so if you ever see that on a quiz or a test, make sure you're including those diagrams. Explain the following stages of the motion when the ball is being thrown up in the air. So first off, you're holding the ball in your hand. Hold in hand. And it's at rest and it stays at rest, right? Then you're throwing the ball upwards. This is where you are forcing / pushing ball upwards. And then the ball flying through the air. So this is now after it has left your hand. And essentially, it's a projectile at this point, thinking back to Unit 2, projectiles. And then finally, the ball hits the ground. I don't think that needs any further explanation. The ball is actually hitting the ground. And we are assuming that there's no air resistance in this one as well. So I would put your video on pause. You got 4 spaces in your workbook to explain these 4 things. Put your video on pause and see if you can explain using at least one of Newton's 3 laws each of these different situations. And when you think you're ready to go, unpause your video and we'll go from there. All right, so we have got these 4 situations. Hopefully you put it on pause. Hopefully you took a bit of time to think about it. Now understand that the way you wrote it out might not be exactly the same as the way I wrote it out, but we should have similar ideas for each of them. So the first section, this is where you're holding the ball in your hand. You're just holding it flat. You're holding it still, contemplating maybe whether or not to throw that ball up. To me, this says Newton's first law. And I know with Newton's first law, because it is at rest and it's staying at rest, the force in the hand must be equal to the force of gravity. So I drew a free body diagram or a force diagram off to the side over here, making my force from the hand on the ball equal but opposite to my force of gravity. We know that that means that the net force is equal to 0, and if the net force is equal to 0, that means it's constant speed, so the ball's at rest, and it will want to stay at rest. So I did this very, very, very point form. That's okay. If you wrote out sentences, that's okay too, as long as the big ideas are there. So perfect. You're just holding something in your hand. It's at rest, and it's going to stay at rest until you decide to throw the ball. And when you decide to throw the ball, you are now applying a much bigger force with your hand. So highlighting that on the side over here, a much bigger force. Force of gravity is the same size realistically, but you've got a larger force from your hand. Again, Newton's second law. And if the force from the hand is bigger, that means that your net force is going to be the same direction as the bigger force. So it's going to be upwards. And if your net force is upwards, your ball is going to accelerate in the same direction as your net force, which is upwards. So your hand is forcing the ball to accelerate upwards, in other words. Cool. Stage 3, the ball is moving through the air. So this one is Newton's second law, and this is probably the thing that people find most confusing. While it's moving through the air, the only force that's acting on it is the force of gravity. So this is very, very important. The only force that's acting on it is the force of gravity. People say, well, then why is it moving upwards? Well, it's still got inertia. Its motion is still upwards, at least to start. But the only force that's acting on it is still gravity. Inertia is not a force, right? It's just a property of matter. So if the only force that's acting on it is the force of gravity, that means that my net force is the force of gravity, and force of gravity is down, therefore the acceleration is down as well. So this, I put a bit of a zigzag line here, zigzag line. So above the zigzag line is pretty, like this is good enough to get you full marks on a question. We could take this one step further though, actually 2 steps further, and that's what I've done below the zigzag line. So taking us back to kinematics, it's slowing down on its way up. So for this section right here, highlighted in red, it's actually slowing down. At the very, very top, it's at rest. And then in the, let's do blue, in this section here, it's actually speeding up on its way down. So slowing and speeding. Now, can we think about why it's slowing down and speeding up in these particular parts? So the first section, on its way up, its velocity is upwards, but its acceleration is downwards. And we know when velocity and acceleration are in opposite directions, we know that it's going to be slowing down. On the way down, its velocity is downwards and its acceleration is downwards. We know it's going to be speeding up on the way down. The other thing that we could do, and we actually looked at this when we were doing projectiles, is if the net force is equal to force of gravity, well, we can expand on both of those things. So net force is mass times acceleration, and force of gravity is mass times gravity. We see that the masses cancel and the acceleration is actually the acceleration due to gravity, which we could take this one step further. If we're on the surface of the Earth, we know that that is actually 9.81 meters per second squared, at least the average on the surface of the Earth. Very cool, right? Very, very cool. So the final step, the ball hits the ground. There were two different laws that spoke to me, Newton's third law and Newton's second law. So Newton's third law is all about the ball applies a force to the ground and the ground applies an opposite force to the ball. Yeah, totally true. Absolutely. So I've drawn my free body diagrams off to the side. I got force of gravity being approximately the same size, but my force from the ground significantly bigger. And you'll notice that this is my free body diagram for the ball on this side over here. I needed to draw a separate free body diagram or force diagram for the ground over here, because remember, those forces act on opposite or different objects. Cool. So that's my Newton's third law. My Newton's second law, explaining why the ball comes to rest or even bounces upwards when it's hitting the ground, comes to Newton's second law. So Newton's second law is, since the force from the ground is significantly bigger than the force of gravity on the ball, and we've got that drawn in our free body diagram up here, is significantly bigger, the net force is going to be upwards, so the acceleration is going to be upwards, so it's going to slow down at first. It was moving fast downwards, and at minimum, it would slow down to 0. Right? It's not a very bouncy ball. It might just hit the ground and stop. If it's a good bouncy ball, it might hit the ground. It might continue accelerating until it's moving upwards if it's a bouncing ball. So Newton's second law. So that's the lesson. It's a bit of a short one. Bit of an easy one, not a ton of math involved with it, but a very, very important lesson actually, being able to explain things that are going on in our lives using Newton's 3 laws. So check out the practice. Honestly, try and relate this to stuff, like if you're taking your dog for a walk or something, try and relate it. Your dog's pulling on the leash is also pulling on the dog, right? You're driving around in your car, think about it. You're brushing your teeth, think about it. Like every single thing that you do can be explained using these 3 laws, which is kind of neat. Anyways, that is it for today. And for this lesson. So again, make sure you're doing practice. Make sure you're asking questions on Google Classroom or to me when you run into a bit of roadblocks. And we'll talk to you again soon. Bye for now, Physics 20s.